326 years ago, on a January night in 1700, the entire Pacific Northwest coastline dropped 2 meters in a few minutes, and a wall of water raced across the ocean and reached Japan in less than a day. The fault that did that has not moved since. This morning, at 53 minutes past 2, a magnitude 5.7 earthquake hit the corner of the planet where that fault begins. 3 more quakes followed. By the end of this video, you will know whether the morning we just had was geology speaking quietly or if it's trying to warn us about something bigger coming. Let's get into it. At 53 minutes past 2 in the morning Pacific time on June 3rd, 2026, a magnitude 5.7 earthquake struck the seafloor 138 kilometers west-southwest of Pistol River, Oregon. The depth was about 10 to 11 kilometers. The German Research Center for Geosciences logged it slightly lower at magnitude 5.5. That kind of cross-agency spread is normal in the first 90 seconds after an offshore event. Within 2 hours, 3 more quakes followed. A magnitude 5.08, 12:45 UTC, 64 kilometers west of Petrolia, California. A magnitude 4.4 to 7:26 minutes later in the same offshore location. And one more moderate event further out to sea. By daybreak, 4 earthquakes of magnitude 4.5 or greater had struck the corner where Oregon and California meet at the edge of the Pacific. All 4 were offshore. All 4 were inside the same complex of plates. And the largest one hit the exact stretch of coast where the most dangerous fault in America has been waiting, silently, for 3 centuries and a quarter. Nobody on land was hurt, no buildings fell, no emergency alerts went out. The fishermen at Crescent City woke up at their normal hours. The morning commuters on Highway 101 drove their normal commutes. If you were not watching the United States Geological Survey feed in real time, you may not have known anything happened at all. But the seismologists who study this part of the world for a living woke up to a set of data points that does not look like nothing. And the rest of this video is about why. The earthquakes this morning hit the Mendocino Triple Junction. It is the geometric corner where 3 tectonic plates collide at a single point. The Pacific Plate, which makes up most of the floor of the Pacific Ocean. The North American Plate, which makes up the continent. And the third plate, the smallest of the 3, the smallest named tectonic plate on the western North American margin, the Gorda Plate. Roughly 200 kilometers north to south, 250 kilometers east to west, about the size of South Carolina. And it is being squeezed from 3 sides at once. The Pacific Plate is shoving the Gorda Plate eastward at about 5 centimeters every year, along a feature called the Mendocino Fracture Zone. The Cascadia Subduction Zone is consuming the eastern edge of the Gorda Plate underneath North America at about 2.5 to 3 centimeters every year. And new oceanic crust is being added to the western edge of the Gorda Plate at the Gorda Ridge, a spreading center 200 kilometers off the Oregon coast. 3 forces, 3 directions, 1 small piece of crust. The result is a plate that does not behave as a rigid block. It cracks internally. It generates its own earthquakes inside its own body. The United States Geological Survey catalog records about 80 magnitude 3 or greater earthquakes a year in this region. About 2 to 3 of those, on average, exceed magnitude 5. The earthquakes this morning happened inside the Gorda Plate. They happened on internal faults inside the small fragmenting slab that sits directly above the locked Cascadia interface. They did not happen on the Cascadia interface itself. That distinction matters, and we will come back to it. The Cascadia Subduction Zone is the fault where the Gorda Plate is being shoved underneath North America. It runs for about 1,000 kilometers, from northern Vancouver Island down to a point off the California coast called Cape Mendocino. At Cape Mendocino, the geology changes. South of Cape Mendocino, the plate boundary becomes the San Andreas Fault, sliding the Pacific Plate past North America for another 1,200 kilometers down to the Salton Sea. The Mendocino Triple Junction sits exactly at the corner where Cascadia ends and San Andreas begins. The last time the Cascadia interface failed completely was on the night of January 26, 1700. We know the date to within hours. We know it because of 3 independent lines of evidence that all agree. The first is the Japanese tsunami record, Coastal villages along the Pacific coast of Japan logged a tsunami arriving on the morning of January 27th, 1700. It was unusual because there was no felt earthquake at the source. The Japanese called it the orphan tsunami because it had no parent. The tax records describing it were preserved in village archives for 300 years before anyone identified the source. The second is the geological record from the Pacific Northwest itself. The 1700 earthquake produced enormous subsidence along the coast. Entire stretches of forest dropped by 1 to 2 meters in a few minutes as the upper plate shifted seaward. The trees that had been standing on dry land found themselves below the high tide line. Saltwater killed them. The decayed stumps and rooted bases were preserved underground as ghost forests. And in the 1980s and 90s, researchers led by Brian Atwater of the USGS and Kenji Satake of the University of Tokyo dated those ghost forests through tree rings and radiocarbon. The dates matched the Japanese tsunami arrival exactly. The third is the indigenous oral traditions of the Pacific Northwest peoples, the Maka, the Quileute, the Yurok, the Hupa, the Tolowa, the Salish-speaking nations of southern British Columbia. The traditions describe villages on the coast swept away by enormous waves that night, canoes carried inland by water that came in after a violent shaking, survivors who moved to higher ground in the aftermath. The detail in those traditions is consistent enough across the affected geography, and consistent enough with the geological and Japanese records, that the academic literature now treats them as a primary source. 3 lines of evidence, 3 different cultures, 3 different methodologies, all pointing to the same night. January 26th, 1700. As of this morning, 326 years and 4 months ago. The Cascadia Subduction Zone has been loading strain ever since. The Gorda Plate has been grinding underneath North America at 2.5 centimeters a year, and the interface above it has been locked, accumulating elastic energy like a steel spring being slowly compressed. That energy has to be released. The question is when. The most thorough work on Cascadia recurrence intervals was done by Chris Goldfinger at Oregon State University, using sediment cores from the deep ocean floor along the Cascadia margin. The cores contain layers called turbidites, sediment deposits from underwater landslides triggered by major earthquakes. By counting turbidites in the cores and dating them with radiocarbon, Goldfinger built a chronology of major Cascadia earthquakes going back 10,000 years. The chronology identifies 41 earthquakes in that window. The average interval between full margin events is approximately 500 to 600 years. The average for southern segment events, the segment that includes the Mendocino Triple Junction, is shorter, in the range of 200 to 530 years. 326 years into the current interval, we are well within the historical range. We are not at the average for full margin events. We are at the upper portion of the range for southern segment events. The United States Geological Survey, in their National Seismic Hazard Model, estimates a 10% probability of a magnitude 9 or greater full margin Cascadia rupture in the next 50 years. The Oregon Office of Emergency Management estimates a 37% probability of a magnitude 7.1 or greater Cascadia event in the next 50 years. Neither number tells you when, within those 50 years, the rupture will happen. The probability in any specific week, including this one, is very small. Not zero, just small. Now we can return to the morning. The Pistol River magnitude 5.7 was inside the Gorda Plate, at a depth consistent with a shallow internal fault. It was not on the Cascadia interface. The Cascadia interface itself, the locked patch underneath North America, was not the source of the energy released this morning. What was released was internal Gorda Plate stress on faults that have been accumulating their own load for thousands of years independent of the Cascadia interface above them. The Petrolia cluster, further south, is more complicated. The events occurred near where the Mendocino fracture zone meets the southern edge of the Gorda Plate. They could be on the fracture zone itself, a strike-slip transform fault running east to west. They could be inside the southern Gorda Plate. They could be on the Pacific Plate side. The formal moment tensor solutions from USGS will be published in the next 24 to 72 hours and will narrow this down. The preliminary depths in the catalog 0.15 kilometers, 0.4 to 7 kilometers are almost certainly artifacts of the autolocation algorithm running on a land-based seismic network with no instruments at sea. The corroborating depth from the European Seismic Agency, 17 kilometers, is more physically reasonable, and the USGS values will be revised towards something in the 10 to 20 kilometer range. So if you saw the USGS website this morning and saw a depth of 0.15 kilometers and wondered if the Earth was about to crack open at the surface, I want to be clear with you. That number was a placeholder. The events were real. The location was real. The depth, as reported in the first few hours, was the algorithm doing its best with limited data. The revision is on its way. A magnitude 5.7 offshore earthquake at 10 kilometers depth on a steeply dipping internal fault produces essentially no vertical seafloor displacement. To generate a meaningful tsunami, you need a large area of seafloor to move up or down by a significant amount. That happens when a shallow thrust fault breaks at a subduction interface, the way the 1700 Cascadia rupture broke. It does not happen when an internal Gorda plate fault slips horizontally at depth. The National Tsunami Warning Center in Palmer, Alaska, runs an automatic evaluation on every offshore event of moderate magnitude or greater. The evaluation for this morning's earthquakes returned the result it was supposed to return. No tsunami threat, no warning needed. The system functioned. The absence of an advisory is not a cover-up. It is the correct scientific conclusion. The December 2024 magnitude, 7.0 offshore Cape Mendocino earthquake, is the most recent comparison point. That event was on the Cascadia interface, not inside the Gorda plate. It was on a thrust mechanism with vertical motion. The algorithm triggered a precautionary tsunami warning. The warning was lifted within 90 minutes when actual sea level observations at the coastal tide gauges confirmed no significant wave. The system erred on the side of caution and then corrected. That is what the system is designed to do. This morning's events did not even reach the threshold for the precautionary warning to trigger, because the events were not the type of events that could plausibly produce a meaningful wave. The most directly comparable historical event happened at this exact location on April 25th and 26th, 1992. A magnitude 7.2 thrust earthquake struck 24 kilometers east of Cape Mendocino on the Cascadia interface itself. Within 18 hours, two large aftershocks followed a magnitude 6.5 at 7:41 in the morning on April 26th, and a magnitude 6.6 at 11:18 the same morning. Both aftershocks were on the Pacific Plate offshore, triggered by Coulomb stress transfer from the original main shock. 500 buildings were damaged. About 100 people were injured. The town of Petrolia, the same town that sits closest to this morning's offshore events, was at the epicenter, and nearly every structure suffered some damage. The 1992 sequence is the textbook example of how a single main shock at the Mendocino Triple Junction can transfer stress across multiple plate boundaries and trigger follow-on events on adjacent structures. It is also the textbook example of how such sequences can dissipate without producing anything larger. The aftershock decay followed the standard Omori law, the rate dropping off by roughly a factor of 10 every order of magnitude in time after the main shock. By the end of 1993, the regional catalog was back to baseline. There was no subsequent major event on the Cascadia interface. There was no large event on the northern San Andreas. The cascade went in the small direction, and then it stopped. There are several features of this morning's sequence that argue against the foreshock interpretation. The largest event came first, and subsequent events have been smaller. Foreshock sequences globally typically show the opposite pattern, accelerating event rates and increasing maximum magnitude in the hours before a main shock. By the time we are putting this video together, the rate of new events in the region has dropped back to roughly the baseline. There is no clear spatial migration toward a single nucleation point. There is no clear depth shoaling. The 5 standard diagnostic features of a textbook foreshock sequence are mostly absent. But the historical record contains a complication. Most events that turn out to be foreshocks do not look like foreshocks while they are happening. The 2011 Tohoku magnitude 9.1 in Japan was preceded by a magnitude 7.3 foreshock 51 hours before the main shock. The foreshock did not look obviously different from a routine, moderate earthquake at the time. The 2010 El Mayor Cucapá magnitude 7.2 in northern Mexico was preceded by a months-long foreshock sequence that was only retroactively identified. The absence of a textbook signal does not rule out the foreshock interpretation. It is consistent with the larger subset of foreshock sequences in the historical catalog, the subset that does not announce itself. The base rate is about 3 to 5% for any moderate offshore Mendocino event being a foreshock to a larger event within 7 days. That is small. It is also not zero. 3 interpretations of this morning sequence sit on the table. Each one has different consequences and different probabilities. The first interpretation is routine activity. The Mendocino Triple Junction produces 2 to 3 offshore magnitude 5 or greater events a year as part of its background rate. 2 such events in a 2-hour window is unusual, but not unprecedented, and has occurred multiple times in the historical record without subsequent escalation. The most likely outcome of this morning's sequence, by a substantial margin, is that nothing further happens. The aftershocks will decay, the catalog will quiet down, the events will become a footnote. Probability of being correct, roughly 85 to 90%. The second interpretation is transient stress redistribution. The morning's events have modified the regional stress field by a small but calculable amount. Coulomb stress transfer calculations would show some adjacent fault patches brought slightly closer to failure, and others moved slightly further away. Under this interpretation, the conditional probability of additional moderate events on adjacent structures in the coming days is modestly elevated, but the probability of a major rupture is not significantly changed. Probability of being correct, roughly 5 to 10%. The third interpretation is foreshock to a larger event. The morning sequence is the early stage of a precursor pattern preceding a major rupture on the Cascadia interface, or the northern San Andreas. The historical analogs exist. The base rate is low. Probability of being correct, roughly 3 to 5%. But the consequences, if correct, are severe enough that the possibility cannot be dismissed. The next several days of seismicity will narrow the picture. The Pacific Northwest Seismic Network will be tracking the regional rate, the spatial pattern of any new events, the deeper interface tremor count, and the GPS stations along the southern Oregon and northern California coast for any sign of anomalous slow-slip activity. The southern Cascadia margin has been in an actively loading state since at least early May, when an episodic tremor and slip episode produced about 153 tremor epicenters on the southern segment. Whether that ETS episode is still ongoing, and whether the morning's offshore events relate to it, are questions that will be resolved in the academic literature over the next several months, but not in real time. What the public-facing data will show, if interpretation 1 is correct, is a quiet rest of the week. The aftershock rate dropping into the baseline, the regional catalog losing the new events as the system absorbs them. By next Monday, this morning will look like just another entry in a 30-year record of offshore Mendocino seismicity. What the data will show, if interpretation 2 or 3 is gaining ground, is the opposite. An accelerating rate, new magnitude 5 class events on adjacent structures, a spatial pattern that migrates toward a single location, tremor counts climbing on the southern Cascadia interface, GPS stations showing anomalous motion. None of those features have been observed at the time we are putting this video together. We are watching to see whether they develop. This morning's events do not change the long-term picture for the Pacific Northwest. The Cascadia interface was loaded yesterday. It is loaded today. The probability of a major rupture in any specific week remains very small. The probability of a major rupture in the next half-century, on the published estimates, remains substantial. The clock has been running for 326 years and 4 months. It is still running. The events this morning did not start it, and they will not stop it. What this morning does change is the operational picture in the short term. The conditional probability of a follow-on moderate event in the next several days is modestly elevated. The conditional probability of a major event in the next week is, at most, a few percent above the very small base rate. That is enough to justify increased attention from the working seismologists. It is not enough to justify changing your morning routine. The practical advice for residents of the affected coast is the same advice the Oregon Office of Emergency Management and the California Office of Emergency Services have been giving for years. Have water, have food, have a communications plan. Know the local tsunami evacuation route from any beach or harbor you visit. Maintain the standard preparedness baseline that the long-term hazard justifies. The baseline does not change because of this warning. The warning is a reminder that the baseline is appropriate. The next major Cascadia rupture, whenever it comes, will be the first full-margin subduction zone event of the modern instrumental era to affect a coastline with dense population, modern infrastructure, and modern emergency response. Every other comparable subduction zone event of the past century, Chile in 1960, Alaska in 1964, Sumatra in 2004, Japan in 2011 happened at coastlines that were either less developed than the Pacific Northwest is today, or were prepared in ways that the Pacific Northwest is not yet. When the next Cascadia rupture arrives, it will be the test case for what modern civilization can absorb from this kind of event. We do not know when it will arrive. We know with substantial confidence that it will arrive within the next several centuries. The morning we just had may or may not be the first whisper of that arrival. The data cannot tell us which. What the data can tell us is that the events occurred in the right place. They occurred on the right system. They occurred at a time in the cycle when the clock is at the upper edge of its historical range for the southern segment. They are inside the distribution of expected outcomes. They are not extreme. They are not unprecedented. They are also not nothing. And the seismologists who study this region for a living went to bed last night with the same long-term picture they have carried for decades and woke up this morning to a small new piece of data that does not change that picture but does, for a few minutes, make it harder to ignore. The aftershock decay will tell us most of what we need to know in the next 24 to 72 hours. We will be watching. The clock keeps running. When the next event comes, whether tomorrow, next year, or in the next century, we will be reporting it the same way we have reported this morning. Direct, calibrated. Without panic and without dismissal, the geology will do what the geology will do. And the work for those of us alive right now is to understand it accurately and prepare for it appropriately. That is the entire job.